Okay, so we're going to go ahead and take a look at our review for Chapter 9, Sections 1 through 3. So I just wanted to make sure that you had something to listen to. I might have you do some of the calculations on your own, but at least kind of do an overview here so we can talk about what's happening. We'll have to go back to Gauss. Hopefully you had a chance to read it. So we know Carl Friedrich Gauss and his wonderful story about the sum of a finite arithmetic sequence or series. Love this. Super important. So that process of how we get there is the most important piece. So he had lots of good things to say about a lot of stuff. So here are the formulas you're going to be able to use. So this is what we're going to be working on. So we have the arithmetic on the left and our geometric on the right. So we'll be using those throughout the day here. So some things that you need to make sure that you know for the test, so you can look this over, knowing those formulas, how they work, recognizing the difference between arithmetic and geometric. So finding a D or finding an R. Make sure you know how to write the terms of a sequence defined recursively. That's meaning you use the previous term to find the next term. So like if you want to find the AK plus 1, you're using the AK term with whatever rule it is going to be to say add 7, whatever it is, or times by 2, then add 7. You use the previous term to generate the next term. So that's what recursively is talking about. And summation notation, that's your sigma. Sigma notation or summation notation, being able to write those. Finding terms and partial sums for arithmetic and geometric, and finding infinite geometric sums, or stating that they do not exist. So making sure that we have an idea of which ones have sums and which ones don't. All right, so we're going to jump right in here. I want to practice and talk about a little bit of each of these and make sure you're okay. I do have answers in the Schoology folder as well for all of these too, if you want to try them first and then check your answers, and you can keep listening as you go, or whatever makes the most sense for you. All right, so write each in expanded form. What does expanded form mean? That means the actual sum, the series. So you're writing out first term plus second term plus third term, or whatever terms you're doing. So remember what sigma means. The number on the bottom, that's your starting term, and the number on the top, that's your ending term. So this is starting with term 0 and going up to term 3, and the rule that you're using is this 2t plus 1. So this is like your nth term formula. It's your an, right? Your a sub n. So it's how we generate those terms. So to get term 0, I'm going to substitute in a 0. To get term 1, I'm going to substitute in a 1. To get term 2, I'm going to substitute in a 2. And to get term 3, I'm going to substitute in a 3. So this is the arithmetic that I would do to generate each of the terms. I'm replacing the t with the value for t for each of those terms. So that's kind of the arithmetic. Here is expanded form. So this is the actual expanded form. I'm going to actually write out that series. So this first term is -3, then we have a -1, and then we have what looks like a +1, and then we have a +3. This is expanded form. Now don't forget to actually do the sum then. Find the sum. This one ends up happening to be 0, so substituting that in. So for each of these, that's the kind of idea that we want to talk about. So for the second one, I want to see if you can do this one. So go ahead and pause the video, and then come back and check in and make sure that you're okay. All right, so I put in starting at term 2, so substituting in a 2 first, and then up to term 5. So I put in 2, 3, 4, 5, did the arithmetic there. This is a quadratic, so it's not arithmetic. This is a degree 2. So the second differences are equal. Remember how we talked about that before? This would be a first difference. And then our second difference is the one that's constant. That's what makes it quadratic. So if you can recognize that, that's awesome. But our sum then is 14. Remember this, actually showing the terms, that's expanded form. So first, well, the second term plus the third, fourth, fifth, and then the actual sum. All right, the last one I want to talk a little bit about, I'm wondering if you notice something different on this one. Infinite sum, okay? So remember, it's hard to do an infinite sum unless it's a geometric with a ratio less than 1, because that would be exponential decay. The terms get smaller and smaller, goes to 0. We can actually do that. So let's take a peek and see if this looks like it's geometric. So I see this a1r to the, right? So we have that definite exponential equation going on. Look where your I is located in the exponent. So it is definitely geometric. Let's see what our ratio is. What are we raising to that power? Well, the r is a half, and the absolute value of 1/2 is most definitely less than 1. What that means is there is a sum, and to calculate the sum, we use our infinite geometric sum formula, which is a1 over 1 minus r. So to be able to do this, we need some information to actually calculate the sum. I have the ratio, which is great. I am going to have to calculate, though, the A1. Well, they wanted me to do expanded form anyway, so I'm going to need to do that. So I'm just going to go ahead and write out the first few terms here. So I'm going to plug 1 in. So 1/2 to the first, and then times 10. Expanded form, I would do, think about how many terms do you think you should do? How far should we go? That people could really actually tell what kind of a sequence or series it is. 2 terms, remember, isn't really enough because we need to be able to check to see if there's a common either difference ratio, whatever it is. So I would probably do the first 3 terms just to be sure people can tell, and then this plus dot, 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 so everybody knows that that's an infinite one. So then we can actually calculate those. So our first term then, 1/2 of 10, that would be 5. And then we have 10 times 1/4, so that would be 10/4 or 5/2. We're just multiplying by 2 in the bottom, so if you kind of see that strategy, that pattern happening, then 5/4 plus dot, dot, dot. So this would be our expanded form. Can't really actually calculate the sum from writing out all the terms there. That's why we're going to use our infinite geometric. So I have my A1 now, that's 5. So I can actually calculate the sum. So 5 divided by 1/2. And remember, dividing by a fraction is the same as multiplying by the reciprocal, so it looks like my sum would be 10. So the only kind of infinite sum, remember, that you can do is infinite geometric with a ratio less than 1. If it was bigger than 1, I wouldn't be able to calculate that sum. All right, so summation notation. Now we're going to go the other direction. So I'm going to give you a sequence, or a series, I should say, so a sum, and I want you to write the sigma notation that would go with it. So what we're trying to do is write that as a sigma. So the first thing first is figure out what kind of series you have. What is the pattern? So it looks like this first one, what are we doing each time here? Looks like we're going up by 3. So if we're going up by a common difference, we have a D of 3. That means this is arithmetic. So this is an arithmetic sequence. The nice thing about that is I have an AN formula for an arithmetic sequence, so I can use that A1 plus n minus 1 times D to help me come up with this rule, this nth term rule that I need to write. That's going to go after the sigma to show people how to calculate that sequence. Remember, what starts in the bottom is just what term you're going to start with. So if I'm writing using the formula, I'm going to start with this as my A1. So I have going from term 1, and then how many terms do I have? Well, term 1, 2, 3, 4, 5. If it's easy to count, fantastic. If it's not, we can use the rule to help us figure out what that last term is. But this one's pretty easy to count up to. That must be term 5. Okay, so how do we figure out the rule? Well, a lot of people just kind of do it by knowing what your D value is. So we know that this is for sure going to be 3 times n. For sure, because my slope is always what the common difference is. What are you going up by? What's that constant rate of change? Now, does that work just by itself? Well, 3 times 1 is 3. If I put in 2, that would be 6. If I put in 3, awesome, it's perfect. So most people can kind of just guess and check there. Otherwise, though, remember, you can use the formula. So to figure out this nth term formula, A1 was 3 times n minus 1 times D, which was also 3. You can literally just simplify this. Always simplify it, too, to make it easier to look at for people. And you're going to end up with the exact same thing. So if you don't like to be creative and it's hard for you to see what's happening, go ahead and just use the AN formula. If you know it's arithmetic or geometric, we have a formula for that, and we can use it for our sigma. All right, so let's try another one here. See if we can recognize this one. So what's the pattern? How do we go from the first term to the second term? Well, it's not adding the same thing. Looks like we're timesing by 5, doesn't it? Each time. So this means we have a common ratio of 5, which means this is geometric. And if it's geometric, again, I have a formula I can use for it, right? All right, so let's talk about our sigma. So if we're going to use the formula, I would start at term 1 for sure. So I'm thinking of this as my A1. And let's use our AN formula for geometric. It's A1 r to the n minus 1. So my A1 is 5. My ratio also happened to be 5, and that would be to the n minus 1. So one way that you could write this would be 5 times 5 to the n minus 1. That's literally using the formula. But a lot of people just look at this and say, hey, wait, isn't that 5 to the first? This is 5 to the second, 5 to the third. So would it also be okay to write this as sigma goes from 1 to whatever? We got to figure out that, of just 5 to the n. 5 to the first, 5 to the second. Well, sure, because if you multiply these with the same base, you would add the exponents, you get n. So either one of these is great. If you like seeing it as a formula, fantastic. If you can just recognize, oh, those are the powers of 5. 5 to the first, 5 to the second, great. How are we going to figure out the number on top? Well, we know what the last term is supposed to be. We know it's supposed to be 15,625. The problem is this little dot, dot, dot in the middle. They didn't show us the whole series, right? So we're going to have to figure out what number that 15,625 is. So let's think about some ways you could do that. Well, could you just keep timesing by 5 until you get there and count how many terms? Sure. If it's a lot of terms later, that would be maybe a long process. What a lot of people do is they just use the formula and they say, okay, if I think my formula is 5 to the n, and I know that has to generate this term, they just can do some guessing and checking and figure it out from there. So I would figure out, okay, what power of 5 is 15,625, and we can just solve for it. So what power of 5 is that? I think it's 6, so it goes to term 6. So you can do either one of those options, and they'll both work great. So if it's geometric, an exponential, we have a formula for that, and we can use it to solve. All right, see if we can figure out this one. Go ahead, pause the video on this one. See if you can recognize, okay, what kind of series is it? And can you write the sigma, and then we'll come back together. All right, so hopefully you recognize that we're going down by 5 each time, so this is a common difference, so it's arithmetic. So I started at term 1, so I just let this be my A1, my term 1. Again, you can do it the creative way, so if I know my slope is -5, it's going to be a -5n for sure, but then -5 times 1, it's -5, that doesn't get me to 24, so 24 plus blank would give me that -5. I'd have to add 29, so that's where the 29 comes from. If that's kind of complicated for you, you don't want to just kind of guess and check, do the formula, which is what a lot of people do. So we have an AN formula. I put in my A1 and my D, simplify that expression, and we can get to this 29 minus 5n exactly the same way. So it's a little bit easier maybe for some people to do. All right, then we have this mysterious dot, dot, dot again, so I don't know how many terms it is. Again, you could just keep subtracting 5. It's not that many more. I think they only left out a couple terms. But remember, you can also use the formula now. You know -1 has to be generated by your AN formula, so just solve for n. Subtract the 29, and then divide by -5, and you're going to get term 6. So that's just a coincidence that the last two were both 6. But we can use the formula, right? So we can either write out the sequence, or the series, I should say, or we can use the formula to help us solve for what that last term is. All right, so one last one. See if we can be creative here. We want to write a sigma for a fraction. Now, remember, we can do different rules for numerator and denominator. So the top and the bottom can have different rules. So in this case, that might be a lot easier to deal with if that's the case, because I can pretty much tell that my numerator is always going to be a 1. Let's say we want to start at term 1. What's happening in the denominator? So again, if we look at what we're going up by, it's up by 3, then by 5. The next one would probably be up by 7, right? Because it's probably going to be over 16, right? And we could keep going. So not arithmetic, no common difference for the first differences, and not geometric. We're not timesing by something, but remember what we just talked about a little bit ago. What if the second differences are the same? What does that mean? Well, that means it's quadratic. So when the second differences are the same, that's a quadratic, or an n squared. So it's going to be some version of a variable raised to the second power. Now, the question is it just n squared? So let's see if that works. So if I plug in a 1, 1 squared is 1. Cool. If I plug in a 2, 2 squared is 4. Plug in a 3, 3 squared is 9. Awesome. So I know it's just n squared. It's the perfect squares on the bottom. What do we go to? So what squared gives you 100? So remember, we can use our rule then to help us solve, and that must be 10. So we can do all sorts of different kinds of rules, but sigma notation is where you're coming up with what is that nth term formula. Okay, let's talk about infinite sequences and series. I'm going to kind of cruise here, but want to cover a lot of ground. Remember, the only kind of infinite series that exists is a geometric when the absolute value of the ratio is less than 1. The terms have to be getting smaller. So your quest is to figure out what your common ratio is. What are you doing to move from one term to the next here and see what kind of ratio you're dealing with? Now, if it's really hard for you to figure out, because you're going to have to type that in, you'd remember when you calculate your ratio, take any term divided by the preceding one. So you could do 15/8 divided by 3/4. And then you can do 75/16 divided by 15/18. That takes a while to type into your calculator. It's totally fine. But how about think of the top and the bottom separately? What are you multiplying by in the top? 3 to a 15? That's timesing by 5. What are you timesing by in the bottom? 4 to an 8, that's timesing by 2. So I am guessing that this ratio is 5 halves. And you can definitely double check it on your calculator. But for me, it's a lot easier to think of fractions that way. And so you can obviously do the division, but look at what the top's doing in the bottom, and then you can put it together for your ratio. All right, so we're timesing by 5 halves. That means our numbers are getting bigger, right? Because we're multiplying by a ratio that is bigger than 1. So the absolute value of 5 halves is greater than 1. What does that tell me? Well, the numbers are just going to keep getting bigger. There's no way I'm going to be able to calculate a sum. So the sum does not exist. And sometimes people put D and E for that, so you don't have to write out the whole thing. The sum does not exist. Why? Because my ratio of 5 halves and the absolute value of 5 halves is bigger than 1. You would have to be able to articulate that, yep, that's why that sum doesn't exist. All right, well, what's the second one doing here then? Let's take a peek. How are we moving from one to the next? Looks like on the top we're timesing by 3, but on the bottom we're timesing by 5. So my ratio then looks like 3/5. Again, remember you can take 6/25 divided by 2/5. 18 over 125 divided by 6 over 25, but probably faster just to look at what the top and the bottom are doing. Well, how do you feel about that? Well, 3/5, that ratio absolute value is less than 1. Why do I keep saying absolute value too? Well, it doesn't matter if your ratio is positive or negative. Negative just means your signs alternate when you look at those terms. If its absolute value is less than 1, those terms, even if they're going positive, negative, are still going to get closer and closer to 0. We would still have a sum. So this is less than 1. That means the sum exists. I can actually do it, and we have a wonderful formula to be able to calculate that. It's A1 over 1 minus the ratio, which we talked about a little bit already. So we have an A1. That's our first term in the series, so 2/5, and then over 1 minus our ratio, which was the 3/5. And then we can just simplify. And this one actually works out really well. 2/5 divided by, looks like another 2/5. So 2/5 divided by itself, this one actually gets a sum of 1. It gets closer and closer to 1. So being able to calculate those infinite geometrics. All right, well, one of the cool applications we did with an infinite geometric was this idea of repeating decimal as a fraction. Remember, this is just a infinite geometric sequence. If we break it apart, you have that common ratio of 1/100th. If it's 2 places repeating, plus ... right, it keeps going. I'm hoping you don't have to do all the work each time, but this is geometric, and its ratio is 1/100th. Which is most definitely less than 1. So then we did our A1 over 1 minus R, and we calculated that out. So we did 75/100ths over 1 minus 1/100th, and you end up, every single time you do this, getting 99 if it's 2 places repeating there. Multiply by the reciprocal. This is all the work that we did before, and you end up with 75 over 99. So what a lot of people start realizing is, oh, however many places repeat, that's how many 9s we're going to have on the bottom. So if 3 places are repeating, what is your guess? Jot down your guess. All right, should be 592 over 999. So just kind of keeping in mind your infinite geometric, whatever your number of places repeating is, that's what your common ratio is. It's just an infinite geometric with a ratio less than 1. So that was a cool application. All right, let's talk recursive for a second. Remember, recursive means where you're using a previous term or terms to generate the next term. So take a look at the notation here. You're trying to find a term a sub k, and you are using the term a sub k minus 1 to solve for it. What's the relationship between a sub k and a sub k minus 1? Well, this term is 1 before that one, right? If I was going to write out the list, a sub k, k minus 1 would come right before a sub k. What would come next? A sub k plus 1, and so on. So if I'm trying to get the next term, I'm using the previous term. That's the relationship between a sub k and k minus 1. So how do I find terms? Well, they're going to have to give you some place to start. So a1 is equal to 3. So the first term I'd be calculating is a sub 2. How do I calculate a sub 2? Well, I take 2 times a sub 1 and then add 5. Because remember, whatever this term is, that term is 1 before it. Well, they gave me a sub 1, so I can actually calculate that. So it'd be 2 times 3 plus 5. So 6 plus 5 looks like 11. So my a sub 2 is 11. All right, well, how am I going to find a sub 3? Well, the third term in the sequence is taking 2 times a sub 2 and then adding 5. So you're taking the answer from the previous and you're going to be plugging it in to calculate the next one. You're always using the previous term. So that would be 2 times 11, the second term, plus 5. So 22 plus 5 looks like 27. So a sub 3 would be 27. Now it says the first 3 terms, so we're good, right? We have the first term is 3, the second term is 11, and then 27. You could keep going. How would you find a 4? Well, you would take 2 times a sub 3 plus 5. We're always taking that previous answer and we're using it to find the next terms. That's what recursive means, taking the previous to find the next one, as opposed to an, which generates all the terms, because you're just plugging in integer values. You can find any term you want. So that's what recursive means. All right, so for the rest of this, I'm going to try to zip through as quick as I can. I know this is kind of long, but we have a lot of stuff here. I want to make sure we talk about finding terms and sums. All right, so let's take a look. We're going to do a little bit of both of those kinds of things. I want you to first pause the video, figure out what kind of sequence this is. Is this arithmetic or geometric? And then choose on which sum formula you're going to use. All right, so hopefully you recognize that this is arithmetic. We have a common difference of -5. So the sum formula I want to use is a1 plus an. Remember, this is Gauss, first and last term, and then how many pairs, n over 2. So let's double check and see what we know. So our n is the total number of terms we're summing. If they say the 32nd partial sum, they mean the first 32 terms. So n is 32. Partial sum, because you could never sum this entire infinite sequence, right? Because it's arithmetic, but we can do part of it, right? We can do the first 32. What else do we need? We need an A1. We definitely have that. That's 7. But we need an AN, and in this case, that would be an A32. I don't have that yet because it didn't give me the 32nd terms. So I need to calculate that. So can you take a moment, pause the video, calculate the 32nd term in this arithmetic sequence? All right, so just to remind you here, the AN formula for arithmetic, A1 plus n minus 1 times D. So 7 is my first term, 32 minus 1 is 31 of these -5. So remember what the nth term formula does for you, it calculates all of those differences at once. So I'm going to do all 31 of those -5s that I need to get to term 32, because every time I move to the next term, I'm subtracting 5 again. It's always one less because you never need that difference for the first term. So we just do that calculation. Hopefully you got -148. All right, so how do we calculate our sum? Well, we'll go ahead and substitute all that in. So the sum of the first 32 is going to be 32 divided by 2, our first term 7, plus our last term -148, and we solve. Remember what these numbers mean. So we have 16 pairs of -141. So if you think about what Gauss did first and last, second and second to last, and added them all up, he noticed that all those sums were the same. All right, so 16 times -141. And we have our sum. So we're going to have to calculate some stuff sometimes, right? We need that last term to be able to calculate that. All right, take a look at this one. I want you to find a formula, an AN formula for the sequence that you're given. So we have to figure out what kind of sequence it is. And then we're going to actually find the 10th term using our formula. So I want you to go ahead and pause the video. What kind of sequence do you think this is? And then write the AN term. All right, so hopefully you notice we're multiplying by a negative number. Do you see the alternating sign, kind of a red flag for geometric here? We're timesing by -3, so the ratio, common ratio is -3. That makes it geometric. So we have our AN formula for geometric is A1, which was 2, times our ratio, which is -3, to the n minus 1. Careful to use parentheses there because we have that negative ratio. All right, now they want you to find the 10th term. So I'm going to go ahead and just substitute in 10 for n. In other words, you're multiplying by -3 9 times, right? Because think of that, you're going to have to multiply each time, subsequent time, so it'll be 9. We don't need a ratio for that first term. I know these numbers are going to get pretty big or pretty small pretty fast, so when we take a look at it, don't be alarmed to see some pretty big numbers, especially when we have ratios bigger than 1. All right, let's take a look at another one. Same kind of thing. So go ahead, pause the video. What kind of sequence do you think it is? And then write your AN formula, and then let's find the 12th term. All right, so hopefully you noticed we're adding 11 each time, common difference, so it's arithmetic. We have our and formula for arithmetic here, so we're just substituting in. A1 was 21, and our common difference was 11. Make sure you simplify. Get this into the easiest format for people to work with, so make sure you simplify. So we have our formula to generate any term I want, and now they want term, oopsie daisy, wow, that went up a long ways. They want term 12, so I'm going to go ahead and substitute 12 into my and just solve. So I'll get my 10th or 12th term here. So it looks like we have 142 for my 12th term. So we can do lots of different things, but we have to recognize what kind of sequence it is first. All right, so back to sum, but again, got to figure out what kind of series it is so we know what sum formula to use. So that's what I'd like you to do first. Pause the video. What kind of sum is it? What kind of sequence? And then which sum formula would you use? Alrighty, so it looks like we're timesing by 3. So we have a common ratio again, so it's geometric. So I have my formula for its sum of a partial sum of a geometric. So S sub n, a1, 1 minus r to the n over 1 minus r. My n here is 10 because they want the 10th partial sum. Again, I can't do the whole thing. It's infinite. The ratio is bigger than 1, but I can definitely sum 10 terms because that's a finite amount. So I can do 10. So let's go ahead and do 10. My a1, my first term in the sequence or series is 14. So I have 14 times 1 minus my ratio, which is 3, to the 10th power over 1 minus my ratio, 1 minus 3. Please make sure you try typing this in. For some reason, just order of operations sometimes gets messed up, but you should end up with 413,336. Again, ratios bigger than 1 are going to generate pretty big sums pretty fast. So have to identify what kind of sequence it is or series, and then we can solve. All right, the last 2 questions we're going to talk about finding out non-consecutive sequences. How do we find ratios or common differences? How do we find other terms from that? Because if they're not consecutive, it's a lot harder to figure out what's happening. So we're going to do geometric first, so you know what kind of series it is or sequence. We want to ultimately find the 8th term. So that's kind of a down the road. That's what we're going to be looking for. And they're going to give you some information about the sequence. They're giving you A11 and they're giving you A13. So I have A11. I don't know A12. Oopsies, I'm going to write it like this. So A12, A13. So I am given this number here, -4. Don't know the 12th term, but I have that as -36. And ultimately, I want term 8, which is back here a ways, right? So we'd have A10, A9, A8. So ultimately, I'm looking for that. Well, in order to figure out any other term, I have to find the ratio. So the first thing I'm going to be looking for is whatever that common ratio is. So I'm going to be looking for R. Remember, any term can be your starting term, and any term can be your ending term, even if it's not starting at term 1. So I would think of this A11 kind of like my A1, and this A13 kind of as my AN, and I can actually use my nth term formula to be able to do that. I'm just going to have to adjust for the length of that sequence. So we talked about this before in that section. So my ending term is the -36. My starting term is the -4. Trying to figure out R. What I need you to adjust is the N. How many terms are in that sequence? Well, there's only 3, not 13, because I know that's a 13th term, but if I'm starting at term 11, that means there's only 3 terms there. In other words, take a peek. When you simplify that, that's r squared. Well, why would it be r squared? Well, to move from term 11 to term 12, I would times by the ratio. To go from 12 to 13, I'd also times by the ratio. So I'm timesing by the ratio twice to get from term 11 to term 13. Okay, now watch what you do to solve. If I solve for r, the first thing you do is divide. So you're dividing the ending term by the beginning term. To figure out the total amount you multiplied by, you have to divide, right, to work backwards. That would give you 9. And then how do you undo squaring? How do you undo that times by r twice? Well, you square root. So if you think back to how we kind of undo the arithmetic, I divide to figure out the total amount I multiplied by, and I take the root that I need to figure out what that number must have been. So it must have been 3. So I was multiplying by 3. So I have my ratio. Now I can find any term that I want in this sequence because I know that my ratio is 3. I'm timesing by 3 each time. So how do I find term 8? Well, I guess you could work backwards, right? So if I'm timesing by 3 to move forward, how would you move backwards? Well, you divide by 3. So I could divide by 3 times to get to my 8th term. So you definitely could do that. I could divide by 3 times. So I could take -4 divided by 3 times, which would be -4 over 27, and you could just kind of do it, right? But couldn't you also use the AN formula? And that's what I want to talk about. Because remember, any term can be your starting term, and any term can be your ending term. You just have to think about where you are in the sequence. Well, A8 comes before either term 11 or term 13. So this is going to be my starting term, and I can pick either of these to be my ending term. I'll just pick the one that's closest. So your starting term is like your A1, and your ending term is like your AN. So the term that I'm trying to find is actually A8. The term that I know is the -4. I have my ratio now, which is a 3, right? And I just have to, again, adjust the length of my sequence because I don't have the full sequence. I'm starting at 8 and going to 11. So how many terms is that? Well, 8, 9, 10, 11, that's 4 terms. So it would be to the -1 power. In other words, you are multiplying by 3 times, right? To go from term 8, 1, 2, 3. So how would you solve for it? Well, think about what we just did then. Didn't we divide by 3 times? It's exactly what we're going to be doing. We're going to divide by that 3 cubed on both sides. So the 8th term would be that -4 over 27. Now, if I was looking for a term after, so like say A17 or something, then I would have been looking for the AN, and the terms that I knew were before it. So just always think about order, small to big. Is the term you're looking for before or after the term you have? That'll determine whether you're looking for the starting term or the ending term. But the whole key thing is figuring out, hey, what's that R? All right, well, we can do the same thing for an arithmetic. So instead of though multiplying by something, what we have to do is find the D. All right, so ultimately we want the 10th term. So we are looking for A10. That is our quest. But in order to do that, we need to find our D. We've got to find our common difference. So we know the 13th term, and we know the 18th term. So sometimes for me, it's helpful to actually visually write that out. We know that this is -6. I've got some blanks in between, and I know this is -51. All right, well, thankfully, we have an AN formula. Some people can just kind of figure this out because they just do the arithmetic. So how far do we have to add or subtract to go from here to here? And then how many of those common differences would there be? So let's just plug the numbers in. Remember, anything can be your starting term, and anything can be your ending term. So think of your term 13 as sort of your A1 here, and your 18th term is your AN. So we have this -51 is equal to the -6. We're going to have to adjust that n. We'll talk about that, and you're solving for D. Okay, the n is what we have to be careful of. If you start at term 13 and go to 18, how many terms is that? 1, 2, 3, 4, 5, 6. So 6 minus 1. In other words, you're adding that D 5 times. Let's think about that. 1, 2, 3, 4, 5. Sure, that makes sense. So how would you solve for that? Well, the first thing that you would do is you're going to work backwards and find that difference. So how far total did we travel here? So -45. And then divide by how many common differences. So in the last one, we did division and root. Now we're doing subtraction and division to undo how many times we added that one on. So it looks like our common difference must be -9. Does it make sense that we have a negative? Well, yeah, the numbers are definitely getting smaller. So now we can do anything we want. We want term 10. Where does term 10 fall? Well, term 10 would be here. We've got a 12 and an 11 in between. So if going this direction, you're subtracting 9, you could just work backwards by adding 9. And how many times did you have to do that? Well, once to get to term 12, another time to get to term 11, and another time to get to term 10. So you could just add 9 3 times, and you're golden. So -6 plus 3 9s will give you your term 10. So you could definitely do that. Or we can do A1, or use our AN formula. I'll just write it this way first. and figure out which term comes first, second, and make sure we adjust that amount. So my starting term, well, term 10 is before term 13, right? You could also use 18, but that's way down the line. So my term 10 is what I'm looking for. My term 13 is my ending term. And I've got to adjust the end, so we'll do that in just a second. And I already solved for D. I know that's a -9. So let's talk about N. If I'm going from term 10 to term 13, how many terms is that? Well, 1, 2, 3, 4. So in other words, let's think about what we've got here. We've got our -6, and we have 3 of those -9s, right? We're adding that -9 3 times to get from term 10 to term 13. All right, so think about the arithmetic you do. So we have A10 minus 27 equals -6. Wouldn't you just add 27? So your 10th term would be equal to 21, which is exactly, if you work backwards, exactly the same thing that you would have gotten. So it's that whole idea of trying to figure out, okay, what's my difference or my ratio, and then using anything as your starting term as long as it comes before your ending term. Lots of things to talk about in Chapter 9. We did a lot of work here. Good things to review and take a look at before the test.